Okay, now I'm recording. Okay, so we're going to start where we left off. So we're on 6.3.2, the mathematical expectation of a function of a random variable. So we're going to start with theorem 6.2, which is let x be a random variable with probability function f of x. Let g be a real valued function defined for values x that are possible values of capital X, or for negative infinity less than x less than infinity. The mathematical expectation of the random variable g of x is the quantity e of g of x. Okay, so please mute your mic. Okay. E of g of x, which is equal to just need this break bracket here. Okay, there we go. E of g of x, which is equal to the sum of all possible values of x of g of x times f of x if capital X is discrete. And it's the definite integral from negative infinity to infinity g of x, f of x, dx if capital X is continuous. Okay, so this is the mathematical expectation of the random variable g of capital X. Okay, so it's split between two cases, right? Either x is a discrete random variable or it's continuous, and so these are values in those cases. So this is provided provided that the series converges absolutely if capital X is discrete, and that the integral is defined if x is continuous. Okay, so you have the e of g of x are these things. If x is discrete, you get the sum, but only if the sum converges absolutely. That means that the sum of the absolute value of the terms is finite. Okay, and it's this integral if x is continuous, but only if this integral is defined. Okay, so let's look at an example. This is example 6.16. Let g of capital X be the random variable of example 6.14. Find e of g of x. Okay, solution. Okay, so let's look at the random variable of example 6.14. So example 6.14 was this. So I'm just going to copy this and bring it over to our other lesson. Okay, so actually I'm going to copy up to here. So bring this back here. So this was example 6.14. So S was the experiment rolling 2 dice. S, here's the sample space, right? I, J, first, second coordinates are the rolls of the die, each are 1 through 6. And so the random variable capital X is the sum of the two die. Okay. And so g of x, though, is the sum of the values of the two die squared. So g of x of I comma j is I plus j squared. So g of x is the random variable that represents the square of the sum of the values of the two dice. Okay, this is the summing. This sums up all of that. Okay, so we are now going to find e of g of x from that example. Okay, so e of g of x. So here x is discrete, right? So here capital X is a discrete random variable because the sample space is finite. Okay, so e of capital G of x is going to equal this sum because we're dealing with the situation where the sum is finite. Right? Just write it in. So this is the sum over all constant values of x of g of x, f of x. Okay, so x, right, are the sums of the values of the two dice. Okay, so the possible values of the sum are so if you roll two dice, the possible values of the sum are 2 through 12, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So x represents the sum. And then g of x is the sum squared, right? So g of x is the sum squared, and then f of x is just the probability of that sum. And so what you want to do is you want to add up these products. And so then, you just add up these possible values. And so we have the probabilities of each thing. So first you have 2 squared times the probability of the sum being 2, which is 1 over 36. Okay. So when the sum is 2, is the probability if the first roll is a 1 and the second roll is a 1. That's 1/6 times 1/6. It's 1 over 36. And so the sum, you take 2 and square it, times 1 over 36 plus, now it's 3 squared times the probability of a sum of 3, which is 2 over 36. Okay, plus 4 squared times the probability of the sum being 4, which is 3 over 36, plus 5 squared times the probability of the sum being 4, which is 4 over 36, plus 6 squared, plus 6 squared times the probability of the sum being 6, 5 over 36, plus 7 squared times the probability of the sum being 7, which is 6 over 36, and that's the most likely sum. Okay, and so that's plus 8 squared times the probability of the sum is 8, but now it goes down. Now it's 5 over 36 plus 9 squared times the probability of the sum of 9, which is 4 over 36 plus 10 squared. We did the example of the probabilities before. 3 over 36 is the probability of the sum is 10. 11 squared times the probability of the sum is 11, which is 2 over 36, plus 12 squared times the probability of the sum is 12, which is just 1 over 36. Okay, so now you get that entire sum. And so now when you calculate the sum of those products, you get 1,974 divided by 36. And as a decimal, that's 54.83. Okay, so that's E of G of X. And that's that problem. Okay, keep going. 6.4 is on theorems on mathematical expectation. So theorem 6.3 says if C is a constant and the expected value of your variable being C is equal to C. If the expected value of a random variable that's always C is C. Proof. Well, if E of C is equal to C, E of C equals C is equal to C times the probability that your random variable X is equal to C. But it's always equal to C because it's C. So C times 1 is equal to C. And so the expected value of a random variable that's always C is just C. Theorem 6.4. Let A naught, A1, A2, and so forth, up to including A sub n, be constants if E of x squared and E of x to the n exist, then E of A naught plus A1 x plus A2 x squared plus A3 x cubed plus plus A sub n x to the n is equal to, A naught plus A1x plus A2, A1 plus E of x plus A2 E of x squared plus A3 E of x cubed plus plus A sub n E of x to the n. So what I did was I just moved the E inside. E of a constant is that constant. E of A, and so E is linear. So E of a sum is the sum of the E's of each term. So you have E of A naught plus E of A1x plus E of A2x squared plus E of A3x cubed plus . But then if you take E of a constant times a variable, you can move the constant out. So E of A1x is the same as A1 times E of x. Okay, see that? Okay, so you get that is equal to that. Corollary. If A and B are constants, then the expected value of AX plus B is equal to A times E of X plus B. Okay? So that's a corollary of that. You can just move the E inside, and then it's E of each term, but E of a constant, E of B is B. Okay, so there's a proof of that, but we need to keep going. Example 6.19. Let capital X be the random variable of example 6.2. Find E of 3 minus 2x and E of x plus 4x squared. Okay, so so in example 2, there were two values for f. So we had a probability function f of x, and so f of x was equal to the following values. It was either equal to 3 or it was equal to 9. And so, but it was, the probability was 1/3 if x equals 3, and the probability was 2/3 if x equals 9. Okay. So this was the probability function of example 6.2. Okay, so this was the example 6.2. We had this PDF. Okay, and then when we find the expected value of x here was the sum over possible values of x f of x, right? So that would be the expected value of x. Now, if we want the expected value of x squared, then you just get the sum here of the same values of x, except here it's x squared. So see the difference? X squared means there's an x squared here. So in this problem, the possible values are 3 and 9. And so you get 3 squared times f of 3 plus 9 squared times f of 9. And so then that's equal to 3 squared, which is 9, times 1/3, plus 81, which is 9 squared, times f of 9, which is 2/3. And so when you do that calculation, you get 3 plus 54, which is 57. That's 57. Okay. 9 times 1/3 is 3. 81 divided by 3 is 27. 27 times 2 is 54. 54 plus 3, 57. Okay. So then if you take, so that's e of x squared. Now, if you do e of 3 minus 2x, that's equal to 3 minus 2 times e of x from this earlier theorem, here, this corollary. So then this is equal to, earlier we found this was equal to 7. Okay, this was from earlier calculations. Okay, from another lesson. Okay, so the expected value is 7. So you plug that in here. So you get 3 minus 2 times 7. And 3 minus 2 times 7 is 3 minus 14, which is negative 11. Okay, so the expected value of 3 minus 2x is negative 11. And now the last one is the expected value of x plus 4x squared. Okay, well, the expected value of x plus 4x squared is e of x plus 4 times e of x squared. See the rules being applied here from these earlier theorems. And so this is equal to the expected value, which is 7, plus 4 times e of x squared, which is 57. And so that's 7 plus 4 times 57, which is 228. Okay, 7 plus 228 is 235. So that's it. Okay, so you can see how applying these theorems, these two theorems and this corollary, we get the expected value from that example of these two expected values. Okay, so next is 6.5, the variance and standard deviation of a random variable. Okay, so you have 6.5.1, which is definition of variance and standard deviation. So definition 6.4. The variance of a random variable, capital X, with mathematical expectation mu is variance of capital X is equal to the expected value of X minus mu squared. So the variance of X is equal to the expected value of X minus mu squared, provided the expected value of X minus mu squared exists. Okay, this is the variance of a random variable capital X. Okay, this is definition 6.5. The positive square root of variance of X is the standard deviation of capital X. Okay, so when you find the variance of X, if you take the positive square root of it, you get the standard deviation of X. Okay, note the standard deviation, which is denoted S dot D dot. That's the notation for it. The standard deviation of a random variable capital X is often denoted by the symbol alpha. Not alpha, oops. Sigma. So I get my alphas and sigmas. This is sigma. Okay, so the standard deviation is often denoted by that symbol, which is called sigma. The variance of capital X is denoted by sigma squared, which makes sense because if you take the positive square root of the variance, you get the standard deviation. So squaring the standard deviation gives you the variance. Right, so if we denote the standard deviation by sigma, then we should denote the variance of X by sigma squared, which we do. Okay. Example 6.20. So in example 6.1, okay, so let me just write. Oh, okay. So if you want to find the variance of X in this example, you have to take the expected value of X minus mu squared. X minus mu squared, right? That's the variance. Now, okay, so for example 6.1, I'll put it down here. Example 6.1 was X is the numerical outcome of one roll of a die. Okay, and so X possible values of X are 1, 2, 3, 4, 5, and 6, and we found that the expected value of X, which is the sum of all possible values of X times f of X. All right, so you get the sum of all possible values of X times f of X. All right, and so we found that that was equal to 3.5. Right, and the possible values of X are 1, 2, 3, 4, 5, and 6. Okay, and the PDF, right? PDF is f of X equals 1/6 for 1 less or equal to X less or equal to 6. So that's example 6.1. So here we want to find the variance in that example. Then yes, what is the mean, right? What is mu? Mu represents the mean, the expected value, which is 3.5, right? So this is mu. Mu is another notation for the expected value. So here you have x minus 3.5 squared. Okay, so the expected value of x minus 3.5 squared, well, it's equal to the sum over all possible values of x. So x could be 1, it goes up to 6, of x minus 3.5 squared times f of x, the probability of each roll. And the probability of each roll is 1/6. And so this is the same as, well, instead of f of x, you put 1/6. Okay. And so you just plug in each value of x equals 1, you get this product, x equals 2, up to including 6, and you add up those products, and when you do the calculation, you get 175 divided by 60, which is equal to 2.917. Okay, and so this is the final answer. So that's the goal. That's good. Okay, so the goal is to find the variance. Okay, let's do another example. So example 6.21. The variance in example 6.4 is, so now we're going to look at example example 6.4. So okay, so let's just do example 6.22, which is the variance in example 6.3 is, so what we want to do is find the variance of x in that example. And so for example 6.3, put here in example 6.3, x was a continuous random variable. The probability density function f of x was equal to 81x squared for 0 less than x less than 1/3. It was 0 otherwise. And so what we found was that the expected value of x in that example, which is equal to the integral from -infinity to infinity of x f of x dx, that's how you compute the expected value of a continuous random variable, you got that was equal to 1/4. Okay, so that was that example. So here, to find the variance, we want to find the expected value of x minus mu squared. Okay, and mu is notation for the expected value. And so this is equal to the expected value of x minus 1/4 squared. All right, and so to find the expected value, you just sum. So if you find this, sorry, it's continuous, so it's integral. And so you want the integral from negative infinity to infinity of, well, x, you have x minus 1/4 squared times f of x dx. Okay, but then what is that? So now what that is it's still that you have the integral from negative infinity to infinity of x minus 1/4 squared. F of x is 81x squared. So it's 81x squared, dx there, but only for 0 to 1/3, 0 otherwise. So I'm going to change this from, it's going to make this 0 to 1/3. So now you just need to compute this integral. And then when you compute that, you get the answer. And so the answer is that that integral is equal to 0.00417. Okay, so you can multiply this out and you can find an antiderivative of the integrand and then evaluate from 0 to 1/3 using the fundamental theorem of calculus. Okay, and you get that value. Okay, regular calculation of an integral, and you get that value. Okay, so that's example 6.22. This is an example of finding expected value from a discrete random variable. This is an example of an example of finding variance with a discrete random variable. This is an example of finding variance with a continuous random variable. Okay. All right. Next is 6.5.2, which is the variance as a measure of dispersion. Okay. So the variance of x is the mathematical expectation of the random variable x minus mu squared for the definition, right? Okay, so it is the expectation of the square of the deviation from the mean of capital X, right? So we're squaring how far away x is from the mean, right? So it's the square of the deviation from the mean of x. Okay, so thus the variance may be looked at as a measure of dispersion. It's telling you how far away each value of x is from the mean. Okay, and the act of squaring it means you make them positive, so you won't get positive and negative values that cancel. Whenever you're far away from the mean and you square it, the further away you are, the larger it is, right? And if you're summing over possible values of x, every value of x adds to the variance. You can't have positive and negative values because you're squaring each term. So the variance can be looked at as a measure of dispersion. Okay, so I'm going to go to the whiteboard quick here. And so this is an important picture, so you should copy this down. Okay, so if you look at mu here, right, this is mu, which is the mean. There's mu. Now, if you look at values within one standard deviation from the mean, so between here and here, then these values are mu minus sigma to mu plus sigma. And so And so if you look at the total area under this bell curve from -infinity to infinity, you can see it can be shown that approximately 68.3% of that area lies here. Okay, so what I'm going to shade in now makes up 68.3% of the total area under the curve. That's 68.3%. That area there. Okay, that's a 68.3%. So that purple region is 68.3%. Now, if you keep going and you go another standard deviation away from the mean, okay, so you go another standard deviation away from the mean. Now, the second one. Now you're mu minus 2 sigma. And mu plus 2 sigma. Right, so now you've got another standard deviation away. Now, if you look at this region, let's make it orange. So now if you look at this region, or this region, these regions each individually make up 13.6% of the total area under the bell curve. So you have 13.6%. So this left orange region takes up 13.6, and this one takes up 13.6. And you see that there is a symmetry going on here, right? Also, the entire purple region takes up 68.3%. And so if you looked at only half of it, this half, the left half, it would take up half of this, 34.15%. And the right side would take up the other 34.15%. Okay, now if you go another standard deviation away from the mean, and you look at this group here, and so you go another standard deviation away from the mean. So now it's mu plus 3 sigma and mu minus 3 sigma. And you look at the region lying here or here, we use red. So now, if you look at this region or this region, they each make up 2.1% of the total area under the bell curve. Okay, so they each make up 2.1% of the total area. And then, if you look at the last region, and we don't section it off anymore, it's just the end. And so it's everything else as this goes out to infinity. Each of these regions make up 0.1% of the total area under the bell curve. Okay? And so this infinite region, meaning that it's underneath the bell curve on the entire real line, right? So in a way, you can't fit this region inside of an arbitrarily large circle because the bottom just keeps going out. It has finite area, okay? It has finite area even though you can't bound it by any circle of arbitrarily large radius, because the bottom thing just really thins out over infinite distance, but it takes up almost no space. Okay, so 0.1% here, 0.1% here, 2.1, 2.1, 13.6, 13.6, 34.15, 34.15. If you add up all the percentages on the right side of this vertical red line, you get 50%. And if you add up all these, you get another 50%. So 34.15 plus 13.6 plus 22.1 plus 0.1. Right, so then 47. Yeah, and then it adds up to 50%. 50% left, 50% on the right. So the whole thing is 100% of the area. And so these are percentages of area under the standard normal density curve, okay? And these intervals are determined by the middle point is mu, the expected value, and then you move to the right or left sigma, which is the standard deviation. Okay, and so this is an important picture, and you should copy it down. Okay, by the purple region, I mean the entire purple region here. These are separated, so I have separate percentages, but the purple one is all together here, and so I counted the left and right side as one piece here, 68.3%. Okay, the whole thing, the left and right side together, 68.3%. Okay, now, okay, so the picture on whiteboard shows the percentages of area under the standard normal density curve. Okay, so that graph of the bell curve, that's a standard normal density curve. Okay. Okay, 6.5.3. 6.5.3. This is, and so this is relating the variance of a random variable to the variance of a set of numbers. Okay. So the variance of a set, capital A, which is equal to contains the elements A1, A2, A3, so forth, up to including the A sub nth one. So the variance of a set A of not necessarily distinct numbers is the quantity. So we want the variance of that set of not necessarily distinct values. And so it's what it is this quantity of the sum from I equals 1 to capital N of, well, you take the deviations from the mean. This is A sub I minus A minus A bar. I'm actually going to copy this because I sometimes don't know how to get this. Like, oh, that didn't do it. Never mind. I'll just have to redo it. Okay. So A sub I minus A bar. That's an A bar. The A bar represents so A sub I minus A bar, where A bar is the mean. Okay. This is where A bar is equal to the mean, which is the sum, which is what you do is you add up. What you do is you add up all the values add up all the values of A sub I over capital N. Okay, so you add up all the values of A divided by capital N, and so this is the mean of the set, capital A. Okay, you add up all the values of A sub I divided by capital N, the total number of elements in the set, and that's the mean of the set. And so here, the A sub I minus A bars, those are the deviations, and then this has to be squared. So you're taking the sum of the deviations, squared deviations from the mean. Okay. And so you're dividing by n because each probability, the probability of each is 1 over capital N. And so it's the sum of each of these times 1 over n, and you just distribute the 1 over n out of the sum each term, and you get 1 over n times the whole sum. Okay, so this is the expected value. Okay, the expected value is the squared deviations from the mean, the expected value, right? So you get A sub I minus A bar squared times 1 over capital N, the sum of that. So you're just factoring out the 1 over n here. Okay, so then, okay, notes. Okay, so notes. This is going to be annoying. The note is that this thing, okay, this thing is equal to minus a bar squared. Okay, if you do some algebra, you can show that this is equal to that. Okay, the possible values of capital X are distinct numbers in set. Capital A, which we denote here as x1, x2, up to including x sub little n. Okay, the a sub i's here, right, are all the terms in set A, but they can be repeated. And so the x's here, x1 to xn, are now these values, but without repetition. Okay. So if you want to know the probability of any of those values, f of x sub I, then right, f of x sub I is the probability of x equaling x sub I. And that's equal to k sub I, which is the number of times that x value is repeated in set A divided by the total number of elements capital A in the set. And I'm just going to write here where k sub I is the number of elements in capital A that are x sub I. Okay. Now, if you look at sigma squared, it's equal to the variance of capital X, which is equal to E of x squared minus E squared of x. Okay. So let me point this out here. So what we said was that the variance of x is equal to the expected value of x minus mu squared, right? So if you square that out, if you do x minus mu squared here and you put it here, you get x squared minus 2 mu x plus mu squared. And then applying the earlier theorems and corollaries, you have that's equal to E of x squared minus 2 mu times E of x plus E of x plus that, plus E of mu squared, which is a constant squared, which is a constant, so it's just mu squared. Okay, so you get this. Now this, E of x is mu. So this is E of x squared minus E of x is mu. So this is 2 mu squared plus mu squared. This is E of x squared minus mu minus mu squared. And so this is the same as E of x squared minus E of x, which is mu squared. Okay, what we're squaring is the E of x. So I'm going to write it as this. I'm going to put this in a bracket. Okay, and we're squaring that. Okay, so the variance of x is e of x squared minus e of x squared. And so that's what this is. Putting the square here means e of x squared. Okay, and so now that's equal to the sum from I equals 1 to n of x sub I squared f of x sub I. Okay, so that's the e of x squared part. And then minus e of x squared, which is the sum from I equals 1 n of x sub I f of x sub I. And then you take the x root value and you square it. Okay. And so if you keep going with these calculations, okay, so then this is equal to the sum now f of x sub I is k sub I over n. Okay, k sub I over n, right? The probability f of x sub I is k sub I over n. That I replaced that with that. And then it's minus this sum squared. Okay, where this is also k sub I over capital N. But you're taking that whole thing and you're squaring it after you subtract it. When you square it, you subtract the square of that. Okay, and so that equals that. And then this is equal to so then okay, so what you're doing here is you're taking each distinct value, x sub I, you're squaring it and you're multiplying it by the number of times x appears. And so reinterpreting that in terms of values of A. These are adding the squares of all the A's in sets, capital A, all the A sub I squares of the original set. Okay, what you're doing is the x's are the distinct values in set A, right? So you're squaring all the distinct values and multiplying it by how many times x appears. Instead of saying, okay, if 5 appeared 3 times, instead of saying 5 cubed times 3, you would say 5 cubed plus 5 cubed plus 5 cubed. So here, the sum of the squares of the A sub i's is like 5 cubed plus 5 cubed plus 5 cubed, instead of here, where it's 5 cubed times 3, the number of times 5 appeared. Okay, so we're just writing it like that. And then minus. And so here, this thing, we're doing the same thing here. They're taking the distinct values of x, squaring them, and then multiplying them by how many times x appears in the set. And so what that is it's the sum of the squares of the A sub i's it's the sum of the squares of the A sub i's here. It's the sum of the A sub i's Oh, okay, sorry, we're here. This is only x of I, because we're subtracting the expected value and you're squaring it. So the expected value is this, and you're squaring it. There we go. And so now we're taking the sum of the values of A, dividing it by capital N, and then we're taking that fraction and squaring it. And so that what that's equal to is you can just combine the two. Well, this sum squared is okay, so then this is equal to the denominator is capital N. They have the same denominator. And so the numerator is then this sum minus this squared. And so when you do the algebra for that, you then get I equals 1 to capital N of A sub I minus A bar, which is the mean, squared. Okay, and so this is the variance of set capital A. That's what we had here. That's the variance of set A. And so the conclusion is, so if capital X is the value of an element selected from set capital A randomly, then the variance of capital X is the variance of the set capital A of numbers. Okay, so X is the random variable that's assigned the value of the set, the value of the element in the set that you choose. The variance of that variable is the same as the variance of this set. That's the point. Okay, so we're done with that example. Let's go to 6.6, which is on theorems on variance. Theorem 6.5. So theorem 6.5 says that the variance of capital X is equal to E of X squared minus E squared of X. And so since that we turned up already, I spoke about that here. So I'm just going to copy and paste this. So the proof of that is right there. Okay, so the variance of X is equal to E of X squared minus E of X squared. Okay, and note that the notation E squared of X is that's notation for taking the expected value of X and squaring it. Okay, so the two there means E of X squared, like that. Okay, theorem 6.6. So theorem 6.6 says that the variance of AX plus B is equal to A squared times the variance of capital X. Little a is the coefficient of X. It's the variance of AX plus B is A squared times the variance of X. B doesn't get involved, so B doesn't change anything. Okay, proof. So by the definition of variance and corollary to theorem 6.4, we get is that the variance of AX plus B is equal to the expected value of well, you have AX plus B minus E so Okay, so let me write this down, and then we'll look at it and see why. So e of ax plus b, what I'm going to do is going to square that. So why is this? So note that the variance of capital X is equal to e of x minus mu squared, right? So that means that instead of x, if you had the variance of ax plus b, then you're replacing x with ax plus b. And so this is equal to the expected value of the quantity ax plus b as x minus the expected value of ax plus b, which is mu of that, right? Which is the expected value of ax plus b. So you're going to take that whole thing and square it. So I'm going to put this whole thing in parentheses here and then square it. So this is the e of x, which is now ax plus b, minus the expected value of x, which is now e of ax plus b. The x minus mu becomes this thing, and you square it in the expected value. And so that's how you get this expression here. Okay, that means that that's equal to that. Okay, so you have this variance of x plus b is equal to that. Now, that equals the expected value of, well, now what I want to do is I want to find out what's inside the braces there. Okay, so what's in the braces being squared. So what you have in the braces are ax plus b minus a times e of x minus b. Okay, so I'm just finding out what's in the braces before you square it. That's equal. So what that's equal to is that's e of, so now simplifying this, the b's cancel, the b and minus b cancel. And so you get ax, which is this, minus a times e of x, which you're squaring in the expected value thing there. And so now what you have is that you have the expected value of, now you're squaring this, right? What are you squaring? So you're squaring a times, but not capital A, lowercase a, times x minus e of x. Okay, so you're squaring that whole thing. So if you square that whole thing, a is being squared. So this is equal to e of a squared times x minus e of x. Then you're squaring the x minus e of x. The a was already squared. Then you move the a squared out. So you get a squared times e of now. So it's e of x minus e of x. Okay, but then what e E of x minus E of x squared is E of x minus mu squared. And so that's just the variance of x. So E of x minus mu squared is the variance of x. So this is equal to a squared times the variance of x. So I showed the variance of ax plus b is equal to a squared times the variance of x. So theorem 6.6 is proved. Okay, and so that means that concludes the proof of theorem 6.6. And that's the note for that theorem. Okay, so that's the end of 6.6. And now let's keep going. 6.7 is on what's called Chebyshev's inequality. So this is theorem 6.7. Okay, so this is Chebyshev's inequality. Okay. Let capital X be a random variable if E of x squared is finite, then for any C positive, we have that the probability of the absolute value of x being greater than or equal to C is less than or equal to the expected value of x squared divided by constant C squared. Okay, that's Chebyshev's inequality. It says, let capital X be a random variable. If E of x squared is finite, then for any positive value C, we have that P of the probability of the absolute value of x being greater than or equal to C is less than or equal to E of x squared over C squared. Okay, so that's Chebyshev's inequality. Now corollary, this is a corollary to Chebyshev's inequality. Let capital X be a random variable with finite mean mu and finite variance sigma squared. Okay, for constants d greater than 0 and k greater than 0, we have a that the probability of the absolute value of x minus mu is greater than equal to d is less than or equal to sigma squared over d squared. That's A. B. We also have that the probability of the absolute value of x minus mu is strictly less than k sigma is greater than or equal to 1 minus 1 over k squared. Okay, so the corollary is let capital X be a random variable with finite mean mu and finite variance sigma squared. For constants d and k that are positive, we have that this probability is less than or equal to sigma squared over d squared, and that this probability is greater than or equal to 1 minus 1 over k squared. Okay, so this is a corollary to Chebyshev's inequality. Okay, now note the corollary is also referred to as Chebyshev's inequality. So the corollary is also referred to as Chebyshev's inequality. Okay, so we got that done. Good. Okay, so next time we will continue. Okay, so next time we will do an example of using Chebyshev's inequality to start class. Okay, so now though, so for homework, I assigned homework 8, I think. So if we look back at last class, at the end of class, I said homework 8 is due next Wednesday. Oh, it's due Wednesday. Okay, it's not even due yet. Okay, so homework 8. So homework 8, this is homework 8. Okay, so it's due Wednesday. So the last section is 6.3.2. Okay, so you can do all of that now. Okay. Okay, and so I'm going to assign another homework on Wednesday. But right now, you just have homework 8 that is due next class. Okay, so homework 8 is due next class, which is Wednesday, 5/3/2021, right? Reminder, test 3 is on, test 2. Okay, test 2, not test 3, test 2. Right, test 2 is on Wednesday, May 12th during class. Okay, starts at 8:00 p.m. Be on time, do not be late, do not miss it. Use the weekly class Zoom link to attend the exam. Also now important announcement. Okay, the final is on, so it's on the last day of class, which is the 17th. So it's on 5/17/2021 during class. Okay, so from 8 p.m. to 9:15 p.m. Okay. Okay, so it covers all the material for the semester, and a review sheet is online on Blackboard. Okay. Okay, so for the final, okay, so you know when the second exam is, it's Wednesday, May 12th, and the final is on May 17th. Okay, last day during class. So that is the last day of class. Okay. So I will return your exams, your test 2 grades by the 17th. Okay. Okay, so you're going to take the second exam on the 12th, and then I will have your grades for that exam by the 17th. Okay, so you'll know how you did. Well, no, so I'm making the exam during class on the last day of class. Okay, so it's not, I'm not doing it on finals week. I'm doing it on the last day of class. Okay, so the final is on May 17th during class from 8 p.m. to 9:15 p.m. Okay, so don't go by other sources. Okay, go by me. Okay, teacher. Okay, the final is on May 17th during class from 8 p.m. To 9:15 p.m. You're welcome. Okay, so I think this explains everything. The final is on this day. Test 2 is on that day. The final covers all the material, right? Test 2, you can look at the syllabus. It will remind you of the material on that exam, right? And I will turn your test 2 grades by the 17th. So when you're taking the final, you know your grade on all the previous exams, okay? Also, so the review sheet is online on Blackboard. I already said that. Okay, so the review sheet for both is on Blackboard. So just stay for just another minute or two. I'm going to go on Blackboard and just remind you how you find these things. Okay. Okay. Can't minimize it. What are they talking about? Oh. Computers. Okay. Just 1 minute. Okay, so let me put this on the screen. Share screen, Blackboard. Okay, so here's Blackboard. And so if you go there, okay, so if you go here, let me go to tests and let me go to, so here, this is already here before, right? If you go to test 2, your practice questions for test 2 and answers to practice questions for test 2. You go to tests and you go to final. There's review problems for the final, there's answers to review problems for final, and there's additional review problems for final, okay? I'm not posting the additional answers to these additional review problems, okay? It's too much more work, okay? I have the answers to these review problems, okay? So you have all of that, so it's quite a bit. Okay, if there's time, I'm willing to stay longer. I'm willing to stay longer after I give the exam on the 12th. I mean, class ends. Class end was when it ends, right? I'm giving you an exam on the 12th, and then when class is over, it's over. So you don't have to stay. But I'm willing to stay longer, though. I don't know if people want me to do that. Okay. If you want me to stay longer on the 12th and answer your questions with the final, I'll do that. Okay. If you don't want to stay, then we won't. It's up to you. Okay. So if you guys want to stay longer after the exam on the 12th and you want me to help you with the final on that day, I'll do it. Okay. Okay, that covers, I think, everything. Anyone have any questions about anything? Okay, then I'll see you next week. I mean, bye. I'll see you on Wednesday. Bye, everyone. You're welcome. Have a good night. Bye.